the fact that you got here means that you all have checked your emails and found out this is the new link for the rest of the quarter. So I guess that's the good news, right? You don't need to worry about me changing it on you one more time. Oh, there will be one exception to that. The Zoom link for the finals will be a different Zoom link, right? But apart from that, normal class, oh, it looks like the last person's arrived, perfect. What was I going to say? Yeah, apart from the finals, that's it. So here goes. Oh, I'm sorry, I get distracted. I'm very easy. We're finishing off the Chapter 9 Part B1. We're looking at sampling distributions, but this time it's for the difference between two population proportions. So I want you to imagine that you've got population 1, and that can be Scottish people, and then you have population 2, and that's American people. And what we're wanting to do here is to find out, is there any significant difference between these two populations for whatever? And in my made up story, it is, do you like watching or playing football? And for the Americans amongst you, soccer, because we call football football. And we had it before you had your football, which annoys the heck out of me, but I can't do anything about it. So we want to find out who likes watching soccer or playing it. And is there any difference between Scottish people and Americans? Well, you're going to get a sample. That's what we do. So our first sample is going to be called P1 hat. And we asked 200 Scottish people, do you like watching or playing soccer? And 150 of them said yes. And then we had, that'll be sample 1. And then we have another sample for the other group of people, the Americans. And in this case, for no particular reason, we asked 250 of them. And let me do a little calculation here, because I want the numbers to be in a certain range. When I find out under all my tons of pieces of paper where I put my calculator. Go figure, I've lost my calculator. Okay. We do. So if we look at these two, just hold on a second. I'm going to be using my calculator a lot today. I have to spend a little bit more time than just superficially looking for it. Well, it's kind of weird that I would lose it because it should never leave my table. Anybody get any ideas? What do you do when you can't find something?
Retrace your steps.
Oh. Found it. It was underneath my keyboard. Go figure. Right. So let's find out what these two sample proportions are. So I don't need one for that one. It's 0.75. And this one here is going to be a little bit ugly, but it was kind of semi-designed that way. And we got, I'm going to call it 0.72, right, to 2 decimal places. And remember what the goal here is. Is there any evidence to show that these two groups are different? Well, superficially, would you agree that there's slightly more Scottish people, 75%, who like to watch soccer compared to Americans? But we know from experience that every time you take a sample, won't this number change? And every time you take another sample from this population, this number will change. So couldn't that difference just have happened by luck, right? By randomness. So we can't just say, P1 is bigger than P2. That guarantees I've proved it. It could well be that there is no distinct significance between these two numbers. So what we have to do is, eventually, we are going to create confidence intervals. And there's a number of confidence intervals that you can create. The three most common ones are 90%, 95%, and 99%. Now, you might be thinking that third one should be 99.7 and that there should be one over here called 67. You remember or 68. Remember the 68, 95, 99.7 rule, right? But we're not going to do it that way. We're going to do a little bit more sophisticated version of that. And so we're going to get 90, 95, and 99. These are the three most common you will ever see if you look at research papers. If you ever get medical papers saying we've proved something, it will be one of these three. Now, if you do a 90% confidence interval on a difference between two groups, as we have here, that means that we're 90% sure that the real difference is in our interval, but there's a 10% chance of being wrong. If you make a 95% confidence interval, you're 95% sure that the interval contains the answer you're looking for. And you have 99. These are by far the most common, but there are others. But we're never going to do them in this class, but just so you know that they do exist. There is a 99.9% confidence interval. Who do you think might want to be that sure? Can you think of any situation where when you say, yep, there's definitely a difference between these two, and I'm 99.9% sure that I'm right? Just another way of phrasing that. What kind of situations would you want to be that sure about something?
Paternity.
Well, yeah, I guess. Am I pregnant or not? Yeah, I think you probably want to be really, really sure about that. Or do I have an illness that's really serious, right? Do I really have cancer? You'd probably want it up there. NASA wants it up there, right? What's the chances that this thing breaks? We're 99.9% sure it ain't going to break is a pretty safe number, right?
We're 80% sure, you know.
Okay, yeah, you could do it that way. I mean, technically speaking, you can create, and we'll show you how to do it. You can create any number you like. Do you want a 62% confidence interval? I'll show you how to do it. You want a 91.5%? Who would want that? But if you wanted a 91.5% confidence interval, we shall do that. Now, we are talking about the confidence interval for the difference in these proportions. So we're going to take this number and take that number away from it, and we want to see what range of values that difference could get. So before we even do this calculation, let's talk a little bit more about how this can happen. Can you imagine, let's just say I got a 95% confidence interval for the difference between the two groups, right? Between P1 and P2. If that interval was 0.03 to 0.06, that is all positive, right? You agree? All of these numbers are positive. Now that means that this is positive. That means this is true. So if you get a confidence interval and all the numbers inside it, right, all these proportions are all positive, then you have proved, at least statistically, that the first guy is greater than the second. In fact, isn't that what we're probably hoping for the Scottish against American combination right now? Great. So if your confidence interval has nothing but positive numbers in it, that means the first guy is bigger than the second. Scots people watch soccer more than Americans. Well, that's one scenario. Pretend it's not this story, but just another story. And in this second story, the 95% confidence interval, P1 take away P2, ends up being negative 0.06 and negative 0.02. Now, do you notice in this case, everything is negative? Great. All the possible, the difference between these two is a negative number, right? Which means that P1 take away P2 is negative, and that means P1 is less than P2. If that happens, you've proved statistically significantly that the first thing is less than the second thing. Because can you imagine sometimes that's what you're at home, is the first group got a smaller percentage than the second group, right? That's something you might want to prove. Is the first group bigger than the second? Yeah, that's something you might want to prove. There is, of course, a third possibility which we don't like, but unfortunately it happens quite a lot. And you find a 95% confidence interval for the first percentage, take away the second. And the answer you get is an interval that looks something like this, 0.02 to 0.03. You see that? Interval has negative numbers in it, but it also has positive numbers in it. Agreed? You will see a phrase in the textbook and some of the homework where they use this word, and the interval contains 0. Right, so that interval has 0 in it, roughly, somewhere in there, there's a 0, right? What conclusion, if any, can you get if the interval, this confidence interval, contains the number 0? So it's got plus and minuses in it. What, if any, conclusion can you make? Any ideas? The difference could be positive, but it could just as likely be a negative number. Okay, here goes it. When this happens, we have inconclusive evidence. That just means we don't know. They could be equal to each other. One could be bigger than the other. One could be less than the other. We have no idea. And that's bad news, because haven't you spent a lot of time and money, and at the end you don't know anything more than you knew when you started. So as far as the difference between them is concerned. So what we need to focus on is, how do we calculate these confidence intervals so that we can come up with one of these three conclusions? I suspect in this case we're going to try and prove this one, just based on the fact, isn't P1 already bigger than P2? So if there's anything going to happen, isn't it going to be this one, right? Be very unlikely that that was proof that this was smaller than that, right? The data is not pointing in that direction. So how to get a confidence interval? And it's going to be for the difference in two proportions. Now we know how to get a confidence interval for the difference in one proportion. What we haven't done is find how to calculate at least the confidence interval for the difference in two proportions. Here's the theory behind it. If you collect two samples, one from this group and one from this group, and you calculate P1 take away P2, right, that guy, If you do it lots of time, the sampling distribution is normal in shape. And its mean is just the difference you can expect, and its standard deviation, which is called the standard error in many situations. And this is the new guy. Can you remember how we got the standard error for just one sample, for P1, right? Wasn't it the square root of P, 1 minus P over N? Remember that? Square root of P times 1 minus P over N. When you want to find the standard deviation, also called the standard error, you are going to have to do a little bit more work. When you look at the formula, isn't it a little bit like the standard error for the first guy added to the standard error for the second guy? Isn't it really just the two things being added together? You see what I'm getting at? Right? The standard error is this ugly square root. Now to finish, once you know the mean, which is the difference between the two, in this case, the difference between these two, and the standard error, which you come from that, then you can create any one of these confidence intervals. So let me choose colors. 90. Then 95. And finally, 99. A 90% confidence interval, you get that by the difference between the two, plus or minus 1 point, well, it depends on which textbook. We're going for 196, the standard error. So this guy here, that's the formula that you can use to get a 90% confidence interval. I'll do blue for this. If you want to do a 95, it's P1 hat, take away P2 hat. Oops. You know, if I was, this guy is 1.96. This guy up here, always get those two mixed up, is 1.64. Actually 1645 if we're being really accurate about things. So apologize for that. So a 90% uses 1.64, a 95 uses 1.96, and the last one in the list, this guy uses 2.5, 8585, depends on what textbook you want to use. You get this guy. Now, if you wanted to use any other confidence interval, like you wanted to use a 62% or an 81%, you couldn't use any of these formula. These are specific ones that we use a lot. And so these ones have kind of been done for us. So to remind you, 1.64 or 1.645 for 90%. It is a 1.96, thankfully. There's only one version for 95. And 99, there's a 2.58 or 2.585, I think, is the other version of that. So far, so good. You got a formula.
Is the first one the 90%?
Yes. So
What
the
is
1.
it? Go ahead.
90% is 1.645 times the standard error. 95% is 1.96 standard error, and 99 is 2.58. You see, the only thing you change is how much you multiply the standard error by.
Mhm.
So these are
you.
3 special numbers. And I'm going to write those guys separate up here. So I'm going to call them Z 0.90, Z 0.95. I'm going to call this guy 0.99. And that's just so I can keep these guys handy. So we got 1.64. Do I want the 5? Yes, I do. And then I want to do 1.96. And then I want to do 2.58. Since they're the only piece that changed, that's the only pieces I need. Okay, so time to go back to our Scotland against America one. First thing I'm going to do now is test to see if I can find confidence intervals. What do I mean by that? I mean, am I allowed to find them? Can you remember there was a test when it was as one sample? And the test went and said that that guy and that guy both had to be greater than or equal to 10, right? Remember that, the 10 test? Well, let's check it out. How many people said, yes, I like football? 150. Because that's basically the people who said yes. Now, how many said no? Well, if 150 said that one, 50 said that one. Would you agree then? Yep, those two work. All we do now is we check for the second sample. And 1 minus them. The same thing. We'll want to see who said yes and who said no. For the Americans, 179 said yes. Oops, greater than 10. 179 said yes, that's good. And who said no? 71. I keep doing that. 10. 71. So that's the 10 test. That's just, you make sure that N1, P1 is greater than 10. Or did the people who said yes, was there at least 10 of them? And the people who said no, was there at least 10? And in that case, we've passed that. That's pretty much all we need to do as a test. If any one of these was less than 10, let's say there were only 5 people that said yes, or 2 people that said no, you should stop there and not do this test. There should be a bit at the bottom that says, why are you not using this 95% confidence thing? And you're going to say, because it fails this test. They're not going to give you questions where it fails, but they will give you some questions where you have to test that it's okay. So that's step 1. Question?
Shouldn't the bottom one be 21, not 71?
179 out of 250.
No, I'm talking about the people who said no for the second, the USA football one.
Right, so 179 said yes, but it was 250 in that sample. That's why it's a little bit bigger. It would be 21 if both have 200. The cool thing is you do not need these samples to be the same size, because that could be a bit awkward, because, you know, a couple of people don't answer and then you have to go out and ask them, and, you know, they can be any size they want, but worth checking. So let's do step 2 then. We've done the check. Oh, by the way, in a lot of questions, you don't need to do this test. They're just assuming that everything's good. But there are some questions where you do it. Right. Step 2 then is you find the difference between the two. In this case, 75% in Scotland, take away 72, and that ends up being a little bit small size. Do you agree? 3% is not very big, but it might be big enough, right? It might be big enough to work. Right? Now we have to calculate the standard error. And I definitely needed my calculator for this guy because the formula is so ugly, or at least big. P1 hat is going to be 0.75. So it's going to be the square root of 0.75, take away 0.25 over a sample size of 200. And then for the Americans, it's going to be 0.72 times 0.28, but over 250. So I'm now going to do all of that in my calculator. And the good news is you can actually do it in one go without needing any brackets, which is surprising, but it's true. So 0.75 times 0.25 divided by 200 plus 0.72 times 0.28 divided by 250. And the answer I get is 0.042. And we're now going to find one of the 3 confidence intervals. Which one do you want me to get? A 90, a 95, or a 99? Any particular preference?
Try 90 first.
Okay, let's try 90%. The formula for getting a 90% confidence interval is the difference between them, plus or minus 1.645 times the standard error. Now, I know the difference between these two. It's 0.03 plus or minus 1.645 times the standard error, which is 0.042. Let's see what we get here. 0.03. I better actually put that down right now. Plus or minus this fella. So 1.645 times 0.042, and the answer I get is 0.069 to 3 decimal places. Now you take this number away from that and you get negative 0.03. Is it 1 or 9? Let's check. I think it's 1. 0.03, take away 0.069, and you get a 9 there. And if you go the other way, you get 0.099. There is our 90% confidence interval. The difference between these two countries is somewhere between -4% and plus 10%, right? I'm just rounding off. -4% and plus 10%. That interval contains 0. Isn't that bad news? Because what does that say? It says it's inconclusive. So we couldn't honestly say that we've proved that Scottish people watch or like football more than Americans, because the difference between these two could easily just have happened with randomness, right? There's no evidence to prove otherwise. Are we cool with it? If I tried a 95 or a 99, all that would happen is that the interval would get bigger and then bigger, and it would be even more inconclusive, right? We wouldn't get any benefit out of making an adjustment to the confidence interval. Okay. So far, so good? Any questions about that one? Okay, let's try one where I'm going to deliberately make sure that there's evidence. So let's have males and self-identified females. And that's going to be population 1, and they're going to be population 2. And what should we ask them? Something I can say that males do more likely than females. No evidence to prove this, but we asked them, do you like watching sci-fi movies? And in the guys, it was 65 out of 80. And with the women, it was 25 out of 100. So really quite small sample size. If I do the 65 divided by 80, and the answer I get is I'll round it off, 0.81. So about 81% of males said that they like watching sci-fi, and for the females, it was only 25. Would you agree that they are hugely different because I made them that way? So with a bit of luck, shouldn't we be able to get proof using confidence interval that this just couldn't happen by just randomness? Well, the difference between the two is 0.81, take away 0.25, which is 0.56. Now we'll get the standard error. I think this is going to be the last time I'll write this formula down. I'll just, in the later questions, I will just put in the decimals. So for the first group, it's going to be a 0.81 times a 0.19 divided by just 80 people. And in this one, it's going to be 0.25 with a 0.75. And that's all going to be divided by 100. Again, I should be able to do this in one big go with a calculator. So I've got a square root of 81 times 19 divided by 80 people plus 25 times 75 divided by 100 people. And this answer is going to come out as 0.06 roughly. I'm going to pick the confidence interval this time. And the one I'm going to pick is the 99% one. So a 99% confidence interval. So we're going to be 99% sure, right, that the interval that we end up with here is going to contain the real value for the difference between them. So it's going to be P1 hat, take away that guy, plus or minus 2.58 times our standard error. And this guy here is 0.56. And it's going to be 2.58 times 0.06. When you're doing homework questions, you might want to be a little bit more accurate than I am, just so that WebAssign is happy with your result. So maybe do things to 3 or 4 decimal places. But in my case, it's 0.56, give or take 0.16 if you round it off. And on this side, 40. And this side, 0.72. Do you notice that everybody in this interval is positive, right? So the difference could be as much as 40%, or it could be even as high as 72, right? When you see an interval that has nothing but positive guys in it, like here. When they're all positive, you've proved that P1 is greater than P2. So we can say statistically, at least, that P1, which is the males, like watching sci-fi more than P2, the self-identified females. And that's how you prove, that's one of the ways at least, you can prove something in statistics. In fact, if I'm being really precise about things, couldn't I say more than just men like watching sci-fi more than women, which is what this is telling us? Couldn't I say 40% more, right? I can even put a number on it. It's not like they like it a little bit more. 40% more males like watching it than females, right? Why 40? Well, isn't that number there also in my interval? And isn't that the smallest one that's in my interval? So I know for at least 40% more in a difference. So you can actually add a little bit more to your statement and say that it's at least 40% more males than females. That's quite powerful, because we now have a way that everyone in the the data processing statistics world has agreed that this is a good structured way of collecting evidence to test if there's a difference between two different groups. Any questions about our second one? Then let's, for my third one, and then we'll look at homework questions. Well, maybe not look at them, but we've covered enough that tomorrow when we look at them will be good, is let's use it in a medical situation. Right. Okay, let's suppose that there's a new drug being tested by a pharmaceutical company, the new drug people. And right now there's an old drug. So let's put a story on it. This drug is used to fight cancer. And the way you very often record successes with cancer is things like what percentage of the people are still alive after the treatment. So a very common one is how many are still alive after 5 years. Another way that you can test the success of a drug is that they're in remission, right? You go and you can't find any cancer cells, right? They're gone, right? You killed them all. That's a good place as well, right? So let's have it in this story that if someone is in remission, they have no sign of that cancer, then that's a success. So what they did is that they collected, say, 400 people. Oops, that's an N1. And they 400 people who've got the cancer, and they randomly split them into two groups. So in this group, you've got seriously ill cancer patients, ones that they've caught very early, some in the middle, whatever that would be. And over here, the same kind of group, right? So because they're random, aren't both of these groups containing a whole spread of that disease, right? From very serious to mild, right? And you don't tell the patient whether they're getting the old pill, right? The old drug or the new drug. The old drug is very often called the control group. And the doctors are treating them, right? Because you use your own local doctor or whatever it is. They don't know which drug they are getting either. So isn't that called a double blind when you do that? You don't know what drug you're getting, and the doctor who's treating you doesn't know. The only person who actually knows who's getting what is the person in control of the experiment. And that's called a double blind. And in the medical world, that is considered the best type of control, right? The best way to collect your data. And let's have in this one here, that P1 hat, and let's say P2 hat and so this guy is 90% success rate, and this one is a, oops, decimal point, is an 8% success rate. Okay, we're going to check, is there evidence to prove that the new drug is doing a better job than the old drug? Would you agree that superficially a 90% success rate is better than an 80? Agreed? But couldn't that be just randomness, right? You don't want to put a new drug out in the market thinking that it will do a better job when it actually isn't, right? It's just as good or bad as the other one. So the difference between the two, oh, I've just realized I've done it the same way, but that's fine. Is that one? And the standard error is going to be 0.9, 0.1 over 200 plus 0.8, 0.2, also over 200. Do a square root, fella. 0.9 times 0.1 divided by 200 plus 0.8 times 0.2 divided by 200. And the answer that we get is 0.035. Okay, now 90, 95, or 99. What would be the best confidence interval to do this, to be sure that when you say something's true, that it really is, as far as you can in the real world? 90, 95, or 99? Which one should you go for?
99.
Yeah. Would you agree in medical world, don't you want to be really sure as much as really sure can be? So 99% would be the going rate. Now, if you were the pharmaceutical company, wouldn't you want to use 90? Because that way you get more of it, you get more successes because of that, don't you? Right. Thankfully, the FDA tells them what they must use. The FDA also tell them that the people who actually deal with the data shouldn't be working for the pharmaceutical company. The data should actually be sent to the CDA, right? CDC, I should say. Why do they do that? Why should it be the CDC that collect the data and not the pharmaceutical company? Why do you think the government says, we want to see the numbers? You don't need to see them. You just tell us the doctors and who you've gave the drugs to, and we'll do the rest. Why did they do it that way? And not the pharmaceutical company collects the data themselves? It's a pretty obvious reason.
Perhaps the pharmaceutical company is biased. They'll make their data better so the product sells better.
You don't, well, they're not going to be able to even sell the product unless they get success out of this, right? You know, for every drug that you know of that goes on the market, there's some ridiculous number like 10 who fail, right? Some of them fail because they have bad side effects. Some fail because They just don't do a good job, right? They don't do as good job as the drugs that are out there. And so it costs a lot of money to develop a new drug. So you can imagine there's a lot of motivation to have evidence that proves it's good, right? And so you take that temptation away from them. So it's going to be P1, P2. Oh, anybody remember what the number is?
2.45. Was it?
Pretty close.
5.8.
2 point something.
5.8.
5.8. Right. Or in some textbooks, 5.85. I'm not, it doesn't matter which one I pick because some textbooks use the other number. I wish they would get together with that little hiccup, but we'll live with it. It really doesn't make a big difference. The interval like wobbles a tiny amount, so it's not really that important. But it does bug me. So it's going to be 0.0. No, it's not. Where's the difference? There it is. It's 0.10 plus or minus 2.58 times 0.035. So it's going to be 0.10. So it's a 10% difference between the drugs, plus or minus 2.58 times 0.035. And the number we came up with is 0.09, which is 0.01 to 0.19. Well, pharmaceutical companies happy, aren't they? Because don't all of these numbers, aren't they all positive? And positive means that P1, the new drug, does a better job than P2, the old drug. Okay. Now, that's statistically significant. There is evidence that the new drug more success rate than the old drug, right? But here is common sense. Could the difference be just 1% more effective? So I guess you then have to say, is it worthwhile to introduce a new cancer treating drug that we only know for sure is 1% effective, 1% more effective? Now, it could be great. It couldn't be as much as 19, but let's be on the pessimist side. Couldn't it also just be 1%? And a lot of doctors would probably say, these cancer drugs are really bloody dangerous and you don't know the side effects and they could actually kill your patient, in the long term because you haven't done, thousands of people being treated. I'm not going to do it. And so a lot of these drugs, if they're not really big, tend to get dropped, not because they're not effective, because they are, or that they're not better, because they are, but they're not better enough to make it worthwhile for people to take the risk on a very dangerous drug. Now, if the answer had been this number, wouldn't you be saying, God, yeah, let's get this drug on the market today? It's 20% more effective, right? 20% more people are going to survive with this new drug, right? It's going to kill the cancer more often. It's going to remove it. Go for it, boys, right? So yeah, statistically, but not that strong. Whoa, statistically significant and really strong. Don't you have to take into account also the numbers in your interval, not just the fact that they're all positive? And my last little thing, do you see this number here, the plus or minus 0.09, which I like percentages, plus or minus 9%. What name do we give to that number? It's got 3 words. What name do you give to that plus or minus 9%? I know I asked this. Say again?
Is it
Margin
the-
of error.
Yes, margin of error. I want you to get so used to that term because trust me, I'm going to be using that phrase a lot over the next couple of weeks because it's one of those things that is very important when you're collecting data. What's the margin of error? If the margin of error is really big, aren't you going to have a hard time getting evidence? Right, because it means that the range of values is going to be huge. And the margin of error, it only cares about one thing. The margin of error only cares about the sample size. The bigger the sample size, the smaller the margin of error. It doesn't care what P1 and P2 are. They don't make a big difference. It's all about size of sample. Right. Last name and bye-bye. I'll hang up.